6.3 is combining power functions. This is going to be a little bit long, but to shorten it, I've added a Desmos lab for you to go look at, so I don't spend a solid 3 pages just trying to sketch graphs for you. A polynomial is going to be a sum of our power functions. So the power functions that we've been talking about so far, if you put them together into an equation, like f of x equals 2x to the 5th minus 3x squared plus 2, each of these in and of itself, the 2x to the 5th, the 3x squared, and the 2 correspond to power functions. The 2 is a constant, so it's 0 degree. The degree of this polynomial is going to be whatever the highest degree is in terms of powers of x. So there's an x to the 5th, an x squared, and the 2 corresponds to an x to the 0 because that gets you a 1. So the powers are respectively 5, 2, and then 0 because there's no x's there. And so the highest power in this particular case is 5, right? So the degree of this polynomial is 5 because that's the highest degree of x that we have. The leading order term is that full term. So whatever term has that degree is the leading order term for the function. It defines the general behavior that that polynomial will have. So in this particular case, that is your 2x to the 5th. Now, knowing these, you can go to the Desmos lab now, but I would just watch the rest of the video because we're going to talk about end behavior, which I do ask you in the lab. I originally had the graphing part right here when I would teach this in class. But if you do the Desmos lab, you should probably do it at the end. So I'll come back to this at the very end of the video. It's going to be a Desmos lab on graphing polynomials, so you'll have a bunch of power functions independently, and then putting those power functions together, and then you can see in the lab how that affects the graph, because that is a big part of this section. It just takes a lot of time for me to graph these things by hand, and you actually get a much better visual if you can play with it yourself. So that Desmos lab, again, you'll go to student.desmos.com, and then the code in this case is a 4, capital C, capital A, capital K, and a capital R. And I'll scroll back. So the other side to the graphing is using everything that we've learned with factoring, and how the factors correspond to our x-intercepts. And so that is what we'll talk about in here before you go to that. Basically what you're going to do is factor your polynomial and then use those factors to determine the shape of the graph. So I'm going to start with an example. F of x equals x to the 4th minus 3x cubed plus 2x squared. Now, I noticed that every one of these terms has at least x squared in it. So I can factor the x squared out in front, and that leaves me with, if I pull x squared out of x to the 4th, that gets me an x squared left over, minus 3x cubed with an x squared factored out is going to be just 1x, so negative 3x, and then 2 times x squared divided by x squared just gets me 2. So I have x squared times x squared minus 3x plus 2. And then I can factor the quadratic that I have here, x squared minus 3x plus 2. I need it to sum to a negative 3 and multiply to a positive 2. Since the multiple is positive and the combination is negative, I know that I have 2 negative numbers that when multiplied together get me a 2, so that's naturally a negative 1 and a negative 2. Since I don't have a coefficient in front of x squared, I can just turn that into x minus 1 times x minus 2. So I have an x squared, an x minus 1, and an x minus 2. From what we've talked about previously, we know that this means we have x-intercepts at the values x equals 0, 1, and 2. So the points 0, 0, 1, 0, and 2, 0 are points on our graph that we can use to graph it. The y-intercept corresponds with that x-intercept at 0, 0, so that doesn't really add another point for this particular case because 0, 0 is an x-intercept and a y-intercept. This is the tricky part, test points. Basically, here's the deal. You know that you're crossing the x-axis, or the curve is crossing the x-axis, at your x-intercepts. So if we look on either side of those intercepts to find out what the function is doing in between those intercepts, we can determine if it goes below the x-axis or above the x-axis. And so what we do is we're checking these values on either side of our x-intercepts to determine the shape of the graph. We know that the only way that a function is going to change sign, going from positive to negative or going from the top above the x-axis to below the x-axis, it has to cross the x-axis for that to happen. So what I'm going to do is just pick values. You don't have to use the same values I'm using, but since we know that we have x-intercepts at 0, 1, and 2, then I need to pick some value that is to the left of 0. So I'm just going to pick -1. I need to pick a value between 0 and 1. Naturally, the simplest one that's between 0 and 1 is going to be 1/2. And then I need another value that's between 1 and 2. Again, 1.5 is probably the easiest choice. And then I need something that's to the right of 2. So I prefer to have integers rather than halves, but we had to pick halves because halves are easier than thirds or quarters or sixths, for example, to evaluate. So I chose 0.5 and 1.5 because I had to pick something that was a decimal. And then when I moved to the right of 2, I could use 2.5, I could use 2.75, could use 3, I could use 4, I could use 5. It doesn't really matter. I just need to pick a value that's to the right. And so I picked 3 because that's the next integer. It's still relatively small, so it should be somewhat easy to plug into f of x. So I'm going to plug each of these x values into the function f of x to determine whether the function is above or below the x-axis when I am to either side of these x-intercepts. So I'll start with x equals -1 and substitute it into the original function, x to the 4th minus 3x cubed plus 2x squared. So if I substitute -1 into the original function, -1 to the 4th just gets me a +1. X cubed, -1 cubed, is a -1, so -1 times -3 is a +3. And then plus 2x squared is going to be 2 times 1, or 2. So that sum is 6, which is greater than 0. That tells me that if I am to the left of 0, 0, I have positive values for f of x. We can do the same between 0 and 1 by checking that 0.5 point. So that's 1/2. 1/2 to the 4th is 1/16. And 1/2 cubed is 1/8 times a -3 gets me -3/8. And then finally plus 2 times 1/2 squared. 1/2 squared is 1/4. 2 over 4 reduces to 1/2. If I sum those, I have 3/16, which gets me, again, another value that's greater than 0 and tells me that it's positive, so it's above the x-axis between 0 and 1. Now, for f of 1.5, I could have done either function, so I'm doing the first two with the original function and the latter two with the factored function. Typically, I actually find that the factored function is the easiest way to go. So my recommendation would be to use the factored function, but just for the sense of, just to actually do both, I'm doing both so that if you're more comfortable with using your original function, you're still totally welcome to do that. You're going to get the same answer. The factored function is just easier to plug in and see immediately if it's greater than or less than 0. So for 1.5, I have, that's also 3/2. So 3/2 squared times 3/2 minus 1 times 3/2 minus 2. So 3/2 squared is 9/4. And then 3/2 minus 1, that's 3/2 minus 2/2, which gets me 1/2. And 3 halves minus 2 is 3 halves minus 4 halves, or negative 1 half. So I see that I have a positive, and a negative. And plus times minus gets me ultimately a negative value, which is of course less than 0, so it tells me it's below my x-axis between 1 and 2. The last point is at whatever is to the right of the x-intercept at 2. So I chose 3, but you could choose 5, right, as I said, or any other value that's to the right. So if I substitute that into the factored form, that's 3 squared times 3 minus 1 times 3 minus 2, or 9 times 2 times 1, which gets me 18. Again, that's greater than 0 and tells me it is above the x-axis to the right of 2. So I've sketched in the graph here with our x-intercepts at 0, 0, 1, 0, and 2, 0. And then using those test points, it was positive to the left. I'll switch to orange. So it was positive to the left, right? That's why all of these are above the x-axis. It was positive between 1 and 2, so that's why this is positive and above the x-axis. It was negative between 1 and 2, and so it dips below, and then it's positive again after 2, so then it again grows off to infinity on the right. So that's what these are doing. I'm checking to see if it's positive or negative to determine a general shape of the graph. So this is a sketch. This is not a perfect drawing of what the heck is happening. And I don't expect it to be, but I want to see you be able to test these points and then sketch an estimate of what that graph looks like based on the tests that you took. I know it is not a very straightforward concept, but I'm hoping that if you go through it, you may have to go through the example that I did a couple times to see exactly what I'm doing and make sense out of it, because I know when I've done it in class, we just end up doing it again and again and again because there's just so much going on, and you really kind of have to see this sketch before all of the pieces come together. We still have more to talk about though. So end behavior is what is happening to your function at the ends of the x-axis. So as you go to plus or minus infinity in x, what is happening to the function f of x? In the graph that we just looked at, you can see that as x goes to negative infinity, your f of x is going to infinity. That's what this arrow off to the left and up towards that, it's growing up the y-axis very rapidly, and you can see that you can kind of make the assumption that if you went all the way off to the right infinitely, it would go all the way up infinitely. So so that would tell us that it's going towards infinity based on that arrow. And as x goes to infinity, so as we go further and further to the right, f of x also goes to infinity. Now, that's what that arrow is implying for the same reasons. Notice that the behavior of this corresponds with the x to the fourth. That's our leading order term. So these polynomials will always have the same end behavior as their leading term. So whatever that is, whether that's an x squared, an x cubed, an x to the fourth, and so forth, it's always going to correspond to whatever that is. In this case, it happened to be an x to the fourth, and an x to the fourth looks like a slightly wider parabola. So at the ends, right, it goes off to positive infinity. So our function also goes off to positive infinity, because that's what x to the fourth looks like. Last thing is modeling with these polynomials. So we'll just do an example with a volume problem of a box. We want to write an equation for the volume of a box that has a square base, and all of its sides, which means those corners, sum to 144 inches. So the sides are these guys here that are sketched in. So I have 1, 2, 3, 4 on top, 1, 2, 3, 4 on bottom. I know it's a square, so I know that the sides are the same. That's why I've labeled them as x and x by x. So I have 4 on top, 4 on bottom. That means I have 8 x's. And then the height of the box is different. So that's my h, but I also have 4 of those. And so what I'm summing are then 4 h's and 8 x's to get 144 inches. That can define a relationship between h and x so that I can actually define the volume directly. So h is then going to be given by 144 minus 8x divided by the 4 that's in front of the h, right, if I solve this algebraically. If I reduce that, that tells me it's 36 minus 2x is how I define h. So if our volume is the area of the base times the height, the area of the base is then x squared, and our height is h. So if I substitute in 36 minus 2x for h, I get a volume equation that's x squared times 36 minus 2x, or 36x squared minus 2x cubed. So now we have a function for the volume. What is the degree of this equation? The highest degree is x cubed, right, for our x's. So it's a degree 3 polynomial to determine the volume. What is the leading term in this case? It's that negative 2x cubed, right? Just going back to our earlier. What are the x-intercepts? Well, you would solve for when your factored form is equal to 0, so x squared and 36 minus 2x. X squared is 0 when x is 0, and 36 minus 2x is 0 when x is 18, because 2 times 18 is 36, and 36 minus 36 gets 0. So the x-intercepts happen when x equals 0 and when x is equal to 18. What is the maximum on that interval? We would have to graph it to figure that out. But if you zoomed in, you'll have the 0 and the 18, and you'll have this nice little arc. So naturally the middle will be the maximum, which is when x is equal to 9, and that gets you 1,458 square inches. What about the end behavior? The end behavior for the leading term is an x cubed, and for a negative x cubed, right, so an x cubed would shoot up here and shoot down, and so that means that a negative x cubed would flip that and would go down on the right and up on the left. But this has more to it, so it has this little bump between, but the end behavior is going to be the same. So naturally, based on this graph, what we're going to see, since these are the only x-intercepts, is this one must come back up and shoot off, and this one must continue down to negative infinity. So as x goes to negative infinity, f of x goes to positive infinity, and as x goes to infinity, f of x goes to negative infinity for end behavior. Please let me know if you have any questions. Oh, and try out the Desmos lab. Let's scroll back to the Desmos lab real quick. Enter code 4CAKR when you go to Desmos to do that lab.